Imagine taking a $250,000 CNC lathe, right? You lock in this massive, heavy cylinder of raw steel, and you just decide to crank the speed dial to the absolute maximum.
Just to shave, what, maybe 3 seconds off your cycle time?
Exactly, just to save 3 seconds. And
Yeah.
within moments, you don't have a finished part. You have a completely shattered cutting tool, a ruined block of expensive steel, and, well, the sound of a very expensive mechanical scream echoing across the factory floor.
Yeah, that is a sound you really never want to hear.
No, absolutely not. So, welcome to today's deep dive. We are taking a snack of highly detailed technical documentation on CNC lathe operations, and we're tackling one of the most, really pervasive and destructive misconceptions in manufacturing today.
Right, the idea that pushing for a faster spindle speed just automatically equals higher productivity.
Yes, exactly. That's our mission today, to completely debunk that.
Yeah.
Because it's just not true.
It's really not. But, the instinct to just go faster is incredibly hard to unlearn. I mean, when you're looking at a backed-up production queue, raw speed seems like the most direct variable you can actually control.
It feels like simple math, right?
More rotations per minute, higher RPM, so mathematically you should finish the cycle faster. But stepping onto a modern manufacturing floor and applying that whole crank it to the max logic, well, it completely ignores the fundamental mechanical and physical limits of heavy machinery.
Which is why this is so critical for you listening right now. Because whether you manage a production floor or engineer parts, or honestly, even if you're just fascinated by how everyday objects are actually made, understanding these limits is basically a masterclass in true efficiency.
Absolutely. Maximizing output isn't about raw speed. It requires this intentional, delicate harmony between the machine's torque, the metallurgy of the parts, and the microscopic wear mechanisms that are actively degrading your tools.
Yeah, and the source material paints a pretty grim picture of operators just blindly chasing those shorter cycle times. They max out the RPMs, and it just results in bins full of scrapped parts and blown budgets.
The classic case of working fast instead of working smart.
Right. So if raw speed triggers that kind of catastrophic failure, we have to look closely at the physics of the cut itself. I mean, metal isn't being sliced like a piece of fruit on these machines.
No, not at all. It is being plastically deformed. It's sheared away under immense pressure.
So we really need to move past this illusion of speed and examine the reality of machine power. The formula governing the lathe's motor dictates everything here, right? Power equals torque multiplied by rotational speed.
That's the golden rule. That equation acts as a rigid mechanical boundary. Because a CNC lathe has a fixed power ceiling from its motor, it only has, so much total energy to distribute at any given time.
So it's a zero-sum game.
Exactly. Because that power limit is fixed, the relationship between torque and RPM operates exactly like a seesaw. If you elevate the rotational speed to the maximum, the available torque just plummets to keep the total power output within the motor's limits.
Wow, okay. So going fast literally robs the machine of its strength.
That's exactly it. And conversely, dropping the RPM allows you to access massive amounts of torque. And in heavy turning operations, torque is the critical currency.
It's the pushing power.
Right. It provides that sheer pushing power required to literally force a carbide tool through hardened steel at significant depths. Without high torque, the cutting tool simply cannot overcome the structural resistance of the solid metal.
It essentially mimics the drivetrain of a manual transmission heavy-duty truck. Like, imagine facing a steep, muddy incline.
Oh, that's a great way to look at it.
Yeah. You don't leave the truck in fifth gear and just pin the throttle to the red line. If you do that, you lack the mechanical advantage to move the weight. The engine bogs down, it stalls, or you just, spin the tires uselessly in the mud.
You're making a lot of noise but going nowhere.
Exactly. You have to downshift into first gear. The engine speed drops significantly, but you multiply the torque at the wheels. That slow, gripping, raw pushing power is what actually forces the heavy vehicle through the resistance.
And exactly the same physics apply inside the enclosure of a lathe. If you attempt aggressive material removal on dense steel forgings with a high spindle speed, you're basically in fifth gear on the muddy hill. You deprive the machine of that necessary pushing power.
So what happens? Does it just stop?
Well, the spindle either stalls mid-cut, which is bad enough, or it induces these violent harmonic vibrations that literally shatter the carbide insert into shrapnel.
Which goes back to the mechanical scream we talked about at the start.
Right. And beyond just preventing stalls, utilizing low speed for high torque cutting fundamentally changes how heat and metal chips are managed.
Oh, right. The heat management is huge in the sources.
It's massive. When you are shearing away heavy layers of steel, the friction generates temperatures that can easily exceed 1,000 degrees Celsius.
1,000 degrees, that's insane.
It really is.
Sure.
So running at a lower RPM gives that intense thermal energy, these crucial milliseconds, to actually conduct into the metal chip itself, rather than soaking entirely into your cutting tool.
So the chip takes the heat away.
Exactly. Furthermore, lower speeds alter the physical structure of the chip being removed.
Yeah, that chip formation aspect is heavily emphasized in the sources. I think a layperson might assume metal comes off a lathe as like dust, right?
Oh, definitely. People think of sawdust.
Yeah, but heavy turning creates these thick, continuous ribbons of razor-sharp metal. And if you spin the workpiece at high speeds during a heavy cut, those ribbons become a massive hazard.
They're incredibly dangerous.
They fly off blue hot and unbroken, and they will immediately wrap around the spinning chuck or the tooling block like like a metallic bird's nest.
And that ruins the surface finish of the part. And it requires the operator to completely halt the machine just to clear the jam.
Which destroys your efficiency anyway.
Right. But by utilizing the proper low speed and high torque, combined with the right geometry of the tool, you literally force the metal to curl tightly and snap into small, discrete pieces.
So instead of a long ribbon, it's like little chunks.
Exactly. Those broken chips just fall harmlessly into the machine bed, and they carry the bulk of that 1,000-degree heat away with them.
Okay, so the physics clearly mandate low speed and high torque to safely shear hard metal and break the chips. But diving into the metallurgy section of our sources, it becomes pretty obvious we can't just mandate one universally low RPM across the board, right?
No, not at all. The optimal speed is very much a moving target. It is dictated entirely by the chemical properties of the workpiece and the specific material of the cutting tool itself.
Right. So let's look at the workpiece material first. The documentation explicitly states that while steel demands slow speeds, soft, ductile metals like aluminum and copper mandate the exact opposite approach.
Yeah, they actually require incredibly high cutting speeds.
Which feels backwards. Why do soft metals need to go fast?
Well, the mechanism behind that requirement involves something called built-up edge, or BUE.
Built-up edge, okay.
Right, so soft materials like aluminum cut easily, but they're highly ductile. Under the localized pressure of the cut, the aluminum effectively pressure welds itself directly to the cutting edge of the tool.
Oh, wow. It just sticks to it.
Exactly. And if the speed is too low, this welded material just builds up. It alters the whole geometry of the cutting edge, dragging against the workpiece, and it basically tears the surface rather than cutting it cleanly.
So you get an ugly, ruined finish.
Right. So operating at a very high RPM generates just enough localized temperature and shear velocity to cleanly sever the chip before it even has a chance to adhere to the insert.
Okay, that makes sense. But if you try that with hard metals?
Total disaster. Substituting titanium or hardened steel into that high-speed scenario completely reverses the outcome. The sheer density of hard metals resists the cut, and those high speeds just generate catastrophic, unmanageable heat.
Which directly brings the composition of the cutting tool into the equation, right? Because the material doing the cutting is the ultimate bottleneck for speed.
It really is. Traditional high-speed steel, or HSS, was the standard for decades in machining.
And the source notes HSS is pretty restricted, right? Like cutting speeds between only 10 and 30 meters per minute.
Yeah, very slow by modern standards.
Really?
And the reason is molecular. If you push HSS past those speeds, the friction generates temperatures around 600 degrees Celsius.
And what happens at 600 degrees?
Well, that is the exact point where that specific steel loses its temper. The microscopic crystalline structure of the tool literally breaks down, it loses its hardness, and the edge physically melts away.
It just melts. Wow. Okay, so what's the upgrade from HSS?
Moving up to a carbide tool changes the parameters entirely. Carbide inserts are created by sintering tungsten carbide particles with a cobalt binder.
So they're much tougher.
Way tougher. They maintain their structural integrity at vastly higher temperatures. That pushes your safe cutting zone up to 30 to 100 meters per minute.
A huge jump.
Huge. And if the application utilizes ceramic cutting tools, well, the physics shift again.
Right, because ceramics handle heat differently.
Exactly. Ceramics are virtually immune to heat degradation in this context. In fact, ceramic tools often require extreme high speeds to intentionally generate massive heat ahead of the cut.
Wait, they want the heat.
Yeah. They use the heat to plasticize the metal so the ceramic edge can just plow right through it.
Okay, let's unpack this for a second. because I am looking at the math provided in the source for calculating these speeds, and there is a glaring contradiction I want to bring up.
Oh, I know exactly what you're going to say.
Yeah, so the text clearly states that soft aluminum demands high surface speeds to prevent that built-up edge from pressure welding to the tool, right? You just explained that.
Yep, high speeds for aluminum.
But the formula for calculating RPM dictates that if I am cutting a massive, like 3-foot diameter cylinder of that exact same soft aluminum, I have to drastically drop the RPM compared to a small 2-inch rod. So why does the physical geometry of the part force an operator to seemingly abandon that high-speed rule for soft metals?
It totally feels contradictory, but it makes sense once you separate the concept of RPM, rotations per minute, from SFM, which is surface feet per minute.
Surface feet per minute.
Exactly. SFM is the true speed at which the actual metal is passing across the microscopic cutting edge of the tool.
Okay, so how is that different from RPM?
Think of a classic vinyl record playing on a turntable.
Okay, I'm picturing it.
The entire record is spinning at a constant 33 rotations per minute, right?
Right.
But if you place the needle on the very outside edge of the record, that needle is covering a vast amount of physical vinyl per second, simply because the circumference of the outer edge is huge.
Oh, I see.
Yeah, but if you move the needle to the innermost track, like right near the label, it covers much less physical distance per second, even though the overall RPM hasn't changed at all.
The outer edge is physically moving faster through space.
Precisely. So if you place a cutting tool against a massive 3-foot diameter aluminum cylinder spinning at 1,000 RPM, the metal at that outer circumference is traveling at a terrifying surface speed.
It's moving like a bullet.
Exactly. It will instantly vaporize the tool. So to achieve the correct surface feet per minute, which is the actual speed limit of the material, you have to slow the machine's RPM way, way down.
But wait, as you cut into the part, the diameter gets smaller.
Yes. As the tool cuts deeper into the part, moving toward the center, the circumference shrinks. So modern CNC lathes actually use constant surface skew programming.
Oh, that's clever.
It really is. The machine automatically increases the RPM as the tool moves closer to the center. It's constantly doing the math in real time to keep the actual surface cutting speed perfectly stable.
Well, that completely resolves the contradiction. The spindle speed drops, but the actual speed the metal collides with the insert remains optimal.
Yep.
So, understanding the absolute necessity of that SFM math, what physically happens at the microscopic level when an operator just ignores it? Because the sources document some pretty severe consequences on the factory floor when operators just dial up the speed to chase those faster cycle times.
Yeah, the most destructive consequence is a phenomenon known as thermochemical wear.
Thermochemical wear.
Right. When the surface speed is too high, the friction generates localized temperatures exceeding 1,000 degrees Celsius at the tooltip, like we talked about earlier. But at those extreme temperatures, mechanical wear is no longer your only problem. You introduce chemical degradation.
Chemical degradation of the metal.
Through a process called diffusion wear, the carbon atoms inside the steel workpiece actually begin to react with the cobalt binder holding the carbide tool together.
Wait, really? The metals interact chemically?
Yes. The heat causes the carbon to migrate, literally leaching the binder out of the cutting tool. So the carbide insert doesn't just chip away, it dissolves at a molecular level, completely losing its precise geometric shape.
It is basically being eaten alive by the chemical reaction triggered by the heat. That's wild.
It really is. And alongside that, the text highlights rapid abrasive wear. The excessive speed turns the hard microscopic inclusions in the steel into essentially a grinding wheel, just stripping the protective coatings right off the carbide.
You know, this really reminds me of driving a high-performance vehicle, but deciding to leave the parking brake fully engaged just to somehow get to your destination faster by pressing the gas harder.
That's exactly what it's like.
Right. The friction immediately glazes the brake pads, it boils the brake fluid, and eventually it just destroys the rotors. Any time you might have saved by accelerating harder is completely negated by the catastrophic damage to the mechanical systems.
And the inevitable breakdown. And the financial ripple effect of that breakdown in a manufacturing environment is just staggering.
Because you're constantly buying new tools.
Well, yes, tooling inserts are expensive, but they are technically a consumable cost. The true hidden hemorrhage of cash comes from the machine downtime.
Ah, right, because the machine isn't running.
Exactly. Every single time an operator has to stop the spindle, unlock the tooling block, swap out a degraded insert, and then touch off the tool to reset the machine coordinates, that $250,000 asset is just sitting idle.
Making zero parts, not to mention the scrap rate.
Right, the scrap rate is
Well,
huge.
yeah, because if thermochemical wear degrades the tool's edge mid-cut, the diameter of the part slowly increases as the tool literally recedes.
Right, the tool's getting shorter as it cuts.
So the machine is actively producing out-of-tolerance parts that will just fail quality inspection and end up right in the recycling bin. Plus, the electricity draw of a machine fighting through a cut with a dull, dissolved tool spikes significantly.
It's wasting power, time, and material.
But the text isn't entirely a doom and gloom scenario regarding high speeds. It does outline specific mitigation strategies where higher surface speeds can be maintained without destroying the setup.
Yes, provided the entire mechanical approach shifts. If cycle time is absolutely critical and speeds must remain high, the depth of cut has to be drastically reduced.
So you just take smaller bites.
Exactly. By taking much lighter passes, you reduce the mechanical shock and limit the volume of heat generated per pass. High-pressure coolant delivery systems also become mandatory here.
Right, you can't just drizzle coolant on it.
No, you aren't just spraying fluid on the part. You are blasting coolant at like 1,000 psi directly at the cutting zone.
Wow.
Yeah, you do that to fracture the chips and literally wash the extreme heat out of the cutting interface before that diffusion wear can even occur.
But there's a catch with that too, right?
Of course there is.
Huh.
Applying that much coolant to a hyperheated ceramic tool, for example, can cause thermal shock and just crack the insert immediately. So every variable is deeply, deeply interconnected.
Which perfectly transitions us to the final critical piece of the puzzle. We've established the dangers and the physics of spindle speed on its own, but spindle speed never operates in a vacuum.
Right, it always has a partner.
It is permanently coupled with its mechanical partner, the feed rate. Finding the perfect harmony between how fast the part spins and how fast the tool moves laterally across the surface, well, that's where true machining efficiency is born.
And blindly increasing both the spindle speed and the feed rate simultaneously creates an absolute nightmare scenario called machine chatter.
Chatter. That sounds bad.
It's awful. Chatter is self-excited harmonic resonance. When the cutting forces exceed the rigidity of the tool or the workpiece, they literally begin to bounce against each other at incredibly high frequencies.
It's just vibrating out of control.
Yeah, the metal physically deflects away from the tool, springs back, and strikes the cutting edge thousands of times a second. It leaves this ruined, washboard-like finish on the metal and will basically shatter a carbide tool almost instantly.
So to avoid that harmonic disaster, the spindle speed and feed rate must be perfectly balanced according to the specific goal of the operation. And the text breaks this down into two really distinct phases, right? Roughing and finishing.
Right. Let's start with roughing. During a roughing operation, the aesthetic finish of the part is completely irrelevant.
You don't care how it looks.
Not at all.
Mm-hmm.
The sole objective is massive material removal. You want to excavate the bulk of the steel as efficiently as possible. To do that, the operator sets a deep depth of cut and a very high feed rate, just forcing the tool aggressively through the material.
But to support that heavy mechanical load,
The spindle speed must be kept low. The focus is entirely on torque. It is like using a bulldozer to carve out the foundation of a site. You need deep, slow, raw power.
okay, so roughing is like taking massive slow bites out of an apple just to get to the core quickly.
That's a great analogy. And then once the bulk material is removed, the operation switches to a finishing pass and the mathematical balance flips entirely.
Right.
The goal now is dimensional accuracy down to the 10,000th of an inch and a perfect mirror-smooth surface. So the bulldozer is basically replaced by a scalpel.
Finishing is like taking a razor blade and shaving off micro-thin slices to make it look perfectly smooth.
Exactly. For finishing, the depth of cut is extremely shallow. It's often just a few thousandths of an inch. The feed rate is slowed down significantly, so the cutting edge barely creeps along the surface, leaving absolutely no visible tool marks.
And what about the speed?
Because the mechanical load is so light now, the spindle speed is cranked way up high. That high surface speed cleanly shears the microscopic layer of metal away without any tearing or dragging, and that is what gives you that flawless, shiny finish.
Now, there is a detail in the source material about finding this perfect balance that I found fascinating. It highlights the profound human element in manufacturing, because long before sensors and digital readouts confirm the parameters, an operator actually has to, quote, listen to the machine.
Oh, absolutely. The acoustic signature of a cut tells a veteran machinist everything about the physics happening inside that enclosure.
Just by the sound of it.
Yeah, a high-pitched, screaming frequency indicates chatter. It tells you the forces are unbalanced, the tool is deflecting, and disaster is basically imminent.
And what if it's a deep sound?
Well, a heavy grinding groan means the feed rate is too high for the available torque, and the spindle is just begging for relief.
But when you get it right,
When the speed, feed, and depth of cut achieve harmony, the sound shifts to this smooth, consistent, tearing hiss. That acoustic stability proves the chip is breaking correctly, the heat is being evacuated, and the machine is operating at absolute peak profitable efficiency.
okay, so what does this all mean? Synthesizing everything we've pulled from these technical documents today for you listening, it comes down to this. The deeply ingrained instinct that faster is always better fundamentally fails on the factory floor.
It really does.
High spindle speeds are an exclusive requirement for soft, ductile metals and light finishing passes. But for the heavy lifting of raw manufacturing, you just have to respect the physics of torque.
Right. You have to calculate your surface speeds to avoid chemically dissolving your tools, and you have to balance your feed rates to prevent harmonic chatter.
Exactly. True efficiency isn't about working fast. It is about working smart and orchestrating this incredibly complex interplay of metallurgy, geometry, and mechanical power.
You know, the reliance on the machinist's ear to detect that harmony brings up an incredibly compelling point about the future of this industry, too.
How so?
Well, we currently rely on the human auditory cortex to interpret those acoustic frequencies of chatter and adjust the manual overrides.
Right, veteran machinists listening to the hiss.
But modern CNC lathes are increasingly being integrated with advanced acoustic emission sensors and real-time spindle load monitoring. It raises a really pivotal question regarding the evolution of the trade.
Oh, I see where you're going with this.
Yeah. As artificial intelligence models become capable of interpreting those exact frequencies and dynamically altering feed rates and RPMs in milliseconds mid-cut, how long until that real-time adjustment is entirely automated?
Wow. Will the veteran machinist's intricate, learned ability to literally listen to the cut soon become a lost art?
Replaced by a closed-loop algorithmic response, it's a real possibility.
That is a phenomenal and slightly terrifying question to leave hanging in the air as we wrap up today. Thank you so much for joining us on this deep dive into the hidden physics of manufacturing.
Thanks for having me.
We really hope this exploration encourages you to question the faster is always better mentality in whatever complex systems you manage in your own world. Because whether you were programming the feed parameters on a $250,000 CNC lathe or just trying to navigate the friction of a massive project at work, sometimes downshifting and relying on raw, deliberate torque is the only way to actually cut through the resistance. Catch you next time.